This is video 5 on second year integration. The aim of this video is to solve integrals by using integration by parts. Okay. Integration by parts is used to solve integrals that don't fit the patterns discussed in previous videos, so videos 1 to 4. So we'll look at an example. Example 1, the integral of x multiplied by ex, or e to the power of x dx. So go through the process of deciding which method to use. So no part is related to another by differentiation. So U substitution will not be useful. There are no fractions. So no partial fractions. That one's fairly obvious. Does not fit the integral of k f dash x over fx dx pattern. None of the other methods work. This leaves us with integration by parts. So integration by parts, the rule is found in the formula sheet, and it's stated as follows: the integral of u dv dx dx is equal to u times v minus the integral of v du dx with respect to x. This bit here is the original integral. That's just a way of referring to the integral that we start with. So one part of the integral will be u and the other part will be dv dx. So x could be u or dv dx, e to the power of x could be u or dv dx. Let u equal x. The reason for doing this is that differentiating x gives 1, which will simplify the integral. In this case, by the integral, I'm referring to this here, which has, as you can see, du dx inside it. So that will become very simple. It's almost like we won't have to write du dx because it's just 1. Should lay out the other parts. So the other part of the integral would have to be dv dx, and that's e to the power of x. Du dx must be 1, as the derivative of x is just 1. To go from dv dx to v, that's undoing the differentiations, that's a small integration of its own, or e to the x just comes back to e to the x. Using the rule, state again here, uv v du dx dx, we can put these parts here together. U is x, v is e to the power of x, minus the integral of v, which is e to the power of x, du dx, which I'll write here, is 1, and then dx at the end. Simplifying a small amount, we don't need to write times 1, and then this is easier to integrate than the original integral, the one we started with, plus c. That's the integral of x to the power, the x times e to the power of x. Do a second example. The integral of x ln x dx. This again doesn't follow the any of the patterns, any of the integration methods that were discussed previously, so it's likely to be solved by integration by parts. Let u equal ln x. The reason for doing that is that we can fairly easily differentiate ln x. We'll end up getting 1 over x, but if we try to integrate it, so if we make ln x equal to dv dx, that's a problem all of its own. It's not impossible to do, but it's a little harder. It's unnecessarily difficult at this stage. So if u was ln x, the remaining part of the integral must be dv dx. So x is dv dx. We integrate that to get v and get x squared over 2. The rule states that we should multiply u and v together. That's u and v minus the integral of v multiplied by du dx one half x squared ln x minus, and then the integrand, the inside of the integral, requires a bit of simplification. X squared over 2 times by 1 over x, we just cancel an x top and bottom, making x over 2 dx. 1 half x squared ln x minus x squared over 4 plus c. That's the derivative, so the integral of x ln x.